everyone, if you're watching this, then you would like to see a recap of our traveling salesman class. So here we go. Of course, we went over the traveling salesman problem today, and we talked about what a heuristic is and why it's so important when dealing with something this difficult. We started by asking, what is an NP problem? And remember, an NP problem is the kind of problem that you can check the solution for in polynomial time, but you cannot find the answer in polynomial time, or at least we think you can't. Now, there might be some clever way to do it, but we haven't discovered one yet, and all signs point to that not being possible. So let's take a look at an example. This is a really famous example of an NP problem. Here you have some houses. You'd like to visit these houses. First thing to recognize is how many different ways can you visit these? If you needed to go to each one and end up back at your house, how many different paths? Well, you can go this way, this way, this way, this way, or backwards the other way, that's 2. You go this way, this way, this way, this way, that's 3, or backwards the other way, that's 4. And the last but not least way is you could go this way, this way, this way, this way, or the other way. Now, is going backwards a different path? I think it's fair to argue that maybe it's not. Then you only have 3 possibilities, but let's just, for the sake of right now, say all of those are different ways to go. Now, the thing to consider is that what is the fastest way to do that? Well, to do that calculation, you need to know the distances between the houses. So from here to here, let's say is 1, and then the diagonals are 2. So obviously the fastest way would be to go in a square. Fair enough, but what if we have lots of houses, hundreds of houses potentially to visit? What's the fastest path then? It turns out this question is NP, meaning it's difficult to figure out in polynomial time. If you wanted to check every possibility, that becomes a factorial problem. What's a factorial problem? Well, a factorial problem is one in which to find the number of possibilities that you have to check, you multiply the number that you have, in this case 2, times the previous number times 1, so you get 2. 3 times 2 times 1 is 6. 4 times 3 times 2 times 1 is 24. You can see how this becomes quickly a ridiculously large amount. In fact, this is worse than exponential time. Factorial time is one of the slowest, quickest growing graphs you can have. When I say slowest, I mean for a computer to solve, it would take a really, really long time as you increase the number of possibilities. So factorial is pretty bad. Now, we still would like to try to solve this problem. Can we do it? Well, again, it's too difficult to actually find the best solution for every time. So something you might want to try instead, since this problem is unreasonable, is a heuristic. A heuristic gives you a good enough approximation to a solution. It's not the exact correct answer every time, but it's a workable answer. It's an answer you can be happy with, even if it's not the best. So many of these kinds of problems you solve using a heuristic. If a problem is intractable, a heuristic can give you a good enough solution. That's fine. So you have an assignment posted here under week 5 called 060401 Heuristics. If you open it up, it looks like this. Navigate to code.org and try out building a path. If you mouse over these bubbles, it'll tell you the distance to each one from your starting location, and then you can decide to which you want to go next. Your task is to come up with an idea for how to best do this. This is not an algorithm because it's not always giving you the best answer, but much like an algorithm, this should be an ordered series of steps that I can apply. So, for instance, probably the easiest one that comes to mind is just go to the next bubble based on whichever one's closest. This one's closest. Great. Then this one's closest. Now we have an awkward situation. There's a tie. The algorithm should anticipate there potentially being a tie and have some kind of guidance for what to do. Maybe we just pick one. So pick this one. So there you go. Now, what's the problem with this kind of algorithm? Well, as you see, I traversed right past this guy right here because there was a shorter option available. And at the end of my traversal, I had to make this really, really long path back to it. So potentially you can get much better results if you are a little bit more clever about your heuristic. So it's up to you guys to come up with how you can best avoid these outlier cases. Some ideas that we came up with in class were potentially going in a spiral, making sure that all the edge nodes are covered first and then working your way in. That could be really powerful. Or potentially dividing the screen into some quadrants and making sure you collect all the nodes in one quadrant before moving on to the next quadrant. That way you never have to come back really, really far. So there's lots of ideas out there. If you would like to read more, there's some high-level heuristics here. These are college-level ideas, so I don't expect you to understand everything in here, but there's some really interesting concepts that I think you guys can grasp. So for instance, this particular algorithm is just picking the shortest path each time. It's not very powerful, but moving on, there's some other ideas that could be good. So I highly recommend you maybe check some of these out and think about how you could implement them into your own heuristic. The assignment is due Tuesday at midnight. Also, please don't forget, because of our return to school or partial return to school, next time we meet will be asynchronous and you will have an assignment to complete all by yourself while I'm setting out back at the school. Thank you very much, and I'll see you guys all next time.